more detail. We've got to compile this whole new command. I'll point at this one. We've got to compile this whole new command. We know how to start. We know that we're going to initialize the new variable with the value of this integer expression. So we say, okay, I'd like to start by doing whatever's necessary to get the value of that expression. And I'm going to give as an exit point the label for what I'm going to do next, what I'm going to do afterwards. Okay, so by the time I get to push, I know the value of that expression is in the first register. Because that's the choice that we made. We said the code for an integer expression always gives back the value in the first register. So I'm trusting that that's happened. So now I know the value of IE is in the first register. Okay, I have got to put it somewhere in memory that we can treat as where the variable x lives. Yeah? So that the command can do whatever it likes with the variable x. And there has to be some reliable way of referring to that location. Because anytime this command uses variable x, either assigning it or looking it up, it's got to find that bit of memory where we put the value. So we've got to find a reliable way of doing that. And we can't, so where are we going to put this thing? It's not practical to keep it in a register, because then we would have to be careful not to use that register. And then what if another new came along? Then we'd have to figure out what else to do. But a sensible place to put it is on the stack. So we're relying on the fact that the stack pointer always tells us the lowest place on the stack we haven't used yet. So we know we can put this thing in the stack at the address pointed to by the stack pointer. That's a safe place to put it. And then we increment the stack pointer. That now means we have taken that piece of memory and it has to be kept safe by other processes. We're now using this location, so we have to say protected. The lowest available space on the stack is now one higher than it was before. With me so far? So we have a stack. Nice to have props. We've just computed the value of our integer expression, and we've decided to put it in the next location on the stack. We now have to say, okay, the stack pointer was pointing to here. Once we've allocated that bit of stack, we have to move the stack pointer to point to the next space we can allocate. Okay, but we've got to figure out a way of referring to x, right? How is the code for the command gonna know which place in the stack it should be manipulating in order to look up or assign stuff to x? Okay, now we know that at this precise moment, once the stack pointer is here, that our x is at sp minus 1. But we just referring to x as the thing that's at sp minus 1 isn't going to work, because we can see that our compile code moves the stack pointer around all the time. So trying to figure out where x is relative to the stack pointer is too damn hard. And that's why it's extremely convenient to have another register, the base pointer, which can act as a stable reference point for stack allocated data. So in this situation, imagine the base pointer is where the table is. And it's not going to move. The stack is going to jump up and down up here, but the table is not going to move. So if we can figure out where this piece of memory is relative to the base pointer, we're laughing. If we can figure out a fixed offset for this storage location from the base pointer, we can always use that to refer to x. So what we need to know is how high, and we need to know at compile time, not at runtime, how high above the base pointer this is going to be. And that will allow us to use BP plus H as the way to refer to X. So that's when I realized, okay, how much stuff has been pushed on top of the stack since the base pointer is a thing the compiler needs as an input. That's an extra piece of information we're going to have to know, and we're going to have to keep maintaining in order to be able to choose the right height above the base pointer when we allocate a new variable. So this h, the frame height, it's an input to the compiler for integer expressions and for commands and for all of these things, which we have to make sure that we keep it consistent with whatever we're doing to the stack. So we assume that at the entry point, h tells us how much higher SP is than BP. And if that assumption's right, then we know that at this point, the stack pointer is the same as BP plus H. And even though we've just moved the stack pointer, BP plus H is still the right, an acceptable way to talk about where we put that value. Okay? So that's one thing. That's what's going on with the frame height. Now, what's going on with the curly braces? That is, and it's a little bit sly, but it's an attempt to make life easy. The compiler, this language maintains for all of your compilation processes a symbol table. What's a symbol table? It's a mapping from program variables to accessors, to ways of talking about places in memory. And what we are saying here, what you can do when you kick off a compilation subtask is that you can use this curly brace notation to extend the symbol table locally. So what we're saying here is when you are compiling this command, you should keep all the symbol table information you already know and extend it with the knowledge that whatever variable x stands for now maps to BP plus h. So we know that in this command, whatever was in scope before is still in scope, unless it happened to be called x. And also this x has come into scope. So we need to know when we're compiling this command about all the variables that already existed, as well as the new one. Is that making sense? Yeah? So what we're saying is, okay, we know all the stuff we already knew about the variables, but we're also telling you how to treat the new variable. So that's what this curly braces are doing. And then we're very careful here. We have to tell this compilation task what to use as the frame height. We are allowed to assume that when we started here, the stack pointer was h above the base pointer. And we are allowed to assume, but we must then keep our promise, that when we reach the exit, the stack pointer will once again be h above the base pointer. We need that assumption, because we need to know that when we reach push, the stack pointer is still h above the base pointer. So if the compiled code for IE messes that up, the h that we were given, that was the height at the start, will not still be the height when we were at push. So this calculation will be wrong. That's why we have to make sure we keep the promise to make that the frame height at the start, at the entry point, is restored at the exit point. Is that making sense? So yeah, so now we know this is okay. We know this is okay because we know that this compiled code doesn't mess up the frame height. And now we have to tell this compilation process the correct frame height for it to use. And you can see that because we've added 1 to the stack pointer used to be h above base pointer, now it's h plus 1 above base pointer. So we have to give a frame height of h plus 1 here. And we also know, because we are promised, that by the time this code reaches its exit, the frame height will still be h plus 1. But to keep our promise, we have to make sure that by the time this code finishes, it's back to being h. And that's why we have to subtract 1 from the stack pointer. But that's okay. Well, all we're saying is that the memory location where the value of x was being kept is no longer being used because x is out of scope now. We've done the thing that was in the scope of x, so we can throw away that value and leave the stack the shape it was. Is that making some sort of sense?
If you were to push two variables, would it just be bp plus h plus 1?
Yeah. And yeah, so for example, if this command itself is another new, that's exactly what will happen, because that compilation process will get the frame height h plus 1 as its frame height.
Mm-hmm. Yeah.
So it'll keep on, if you just think of a whole bunch of news in a row, each will get called with the next frame height, and we'll get bp plus h, your bp plus 1, bp plus 2, bp plus 3, and so on. Okay.
See at the pop stage, would you not need to remove the x from the symbol table?
That's automatic,
Oh.
right? When you do this, this is saying locally only for this compilation task is x in the symbol table. So yeah, so the symbol table is treated like an input. It's not kind of mutated. We haven't overwritten the old symbol table. So the symbol table for the compilation as a whole is fixed. But we can say locally adjust it for a subtask. So that's what's going on here. And that fits with the way variable scope works. I mean, that's a choice on my part. Right. Will we hold a revision lecture? Damn right we will. And I think that's that.